Hi everyone, this is a little video for the advanced students of Mechatronics 3100 to help them achieve the final stages of the project. So this is a video of my project from last year. As you can see, it's fairly reliable and it doesn't hit any walls. So that's what I'm going to talk about today. Firstly, how do you drive an accurate distance? You probably already know this, but you want to use two PIDs to control the distance traveled by each of your motors. So what that includes is measuring the encoders, measuring the number of ticks traveled by the encoder, and converting that into physical distance using your R and L values. Alternatively, you can control the PIDs based on encoder ticks only. So that would be converting your 250 millimeters between cells into a number of encoder ticks. And that is actually a more accurate and tunable method of doing it. But that's not what I did in my project. And if you need a little bit of pseudocode, here it is. So just zeroing your encoders, reset your PID integrators, set your PID constants and your set point. So in this case, we're using a step response set point, and it's going to look like this. So we're telling our encoders that we want to travel a certain distance at the start, and we are asking them to get up to that distance based on our KP and KI values. So you will need to tune your KP, KI, and KD if you want to use a KD in order to get a relatively smooth response. But you'll always have a lot of acceleration at the start because it's a step response. So you'll just need to be careful to tune your KP and KI so that you avoid any wheel slippage. Something to note is I did not use a KD in mine. I found that it brought in a lot more instability than it did helping out the project, but you're welcome to try it. And then the rest of this is pretty self-explanatory. We'll talk about other options to this in later on as well. So next, what happens if your car does not drive straight? So one motor might stop or stop before the other one. How do we fix that? The way that I did it is I added an IMU PID to control the heading. But something to note is that this must be disabled at the end of your encoder PID loop. Otherwise, they will fight with each other. Your heading PID will be trying to turn you in a certain direction, and your encoders will detect a change because the wheels are moving, and then it will have to turn the other way. So they will contradict each other and they will cause a lot of oscillations, and the final position will not be correct. So what does that look like in code? So this is what it looks like in code. I've taken out all of the encoder stuff, so it probably doesn't make a lot of sense by itself. But first you set your PID values. Next you set the set point, and then the same thing as before, we do a loop. Note that this does not include the heading PID. We just have this here. Um, yeah, but you need to set this to be 0 if your trajectory is close to being finished. And I'll talk about how I did that later on as well. So, what is this block of code that I deleted earlier? Well, what happens if your IMU drifts while you're moving forward? And it will do this. Then your car, instead of driving straight, it will slowly drift and hit a wall eventually. So the way that you do this is you have to get some feedback from your environment. You have to detect, and you can do it by detecting a wall and adjusting your IMU set point accordingly. So if you're detecting a wall on the left, then you want to make your car drive right a little bit. Um, Alternatively, instead of changing the set point, you can have a bias and subtract the bias from the IMU your input. But it's basically the same thing. Okay, so that is my next 2 points. Also, an alternative to the IMU PID is encoder velocity control. So making sure that both of your motors are the same or similar speed throughout the motion. However, I was not able to get that to work when I did the project. Okay, next one. What happens if your car finishes its motion and it's not in the right spot? It needs to drive forward or backwards a little bit. Well, this could be caused by the fact that the maze's distance between cells is not 100% consistent. Also, it could be caused by motor dead zone and encoder accuracy, which basically limits the precision of your forward motions, and over time that error will build up. So how do we get some feedback into our controller to prevent this, to allow us to account for these error buildups? Well, you can use your LiDARs to detect the wall position and adjust the position of your car as a result. So what we did is, you can probably see it in this video here. So after our car drives forward, then it stops, and that's its filling. It has finished the forward motion, but the LiDAR at the front detects the distance is too far away from this wall here, and then it will run another PID in order to drive forward. So I'll just run that again. So it drives forward, and then it drives forward again. So that's one way of doing it. Another way would be to incorporate the forward LiDAR into your move forward function, so that instead of having to come to a stop and then do another PID after that, it will just do it all in one motion. That would be the ideal way of doing it. Um, so my PID actually used the LiDARs as the input and not encoders, encoder ticks. But it's up to you how you want to implement this. The point is that you just need to detect the environment and use that feedback in order to adjust your car's position. Okay, last point. How do we prevent this wheel slippage? Um, so what I was talking about before is the way that most people do it. They have a step response or a step input, and then they tune their KP, KI, KD in order to prevent most of the slippage. But the issue with this is that, number one, it can only travel a set distance every time because your KP and KI doesn't change. And two, if there's a little bit more sand or dirt on the maze, it'll cause your wheels to slip if you've tuned this to be just right. So what I would recommend is a changing set point. The way that I did it was I did a cubic changing set point, but I would actually recommend a linear changing set point. And the reason for that is that it's easier for your PID uh, controller to catch up to this linear set point than it is to catch up to this cubic set point. So what this allows you to do is reduce this acceleration at the start quite a lot. So instead of asking your motors to go directly from 0 to 250, you're asking them to go at this certain rate, and then your controller is able to do that. I don't have any code to show you for this because this is a bit more advanced and I don't want to get done for plagiarism, but that's the general idea. So you want to change your set point throughout the forward motion. And ideally you want to avoid these big changes of acceleration.